Welcome to part 3 of our module 3 or unit 3, which is sensation and perception. Today what we're going to be talking about is visual organization and interpretation. So our last video, what we talked about was vision as just a sense really, and how it's collecting data, what the different parts of the eye are, and how we then take that electromagnetic energy and turn it into a neural impulse. That way our brain can understand it. What we're going to be doing today is basically the next step of that, where once that information is into our brain, how does our brain organize it and interpret it to make it meaningful? So there's a lot of different things we're going to talk about here. One example of one of the ways we're going to do this is actually on our screen right now. So what we really want to do today is try and pull apart what is our brain doing to add meaning to what the information our eyes are collecting. And the way we're going to do that for the most part is using things like optical illusions or little tricks to try and figure out what the brain is actually doing. So one example of that is this image on the left here. So if you can see the question at the very bottom, it says, are the lines straight or are they curved? And they're talking about the lines right here, these lines. Are they straight or are they curved? So when you look at this image, if you've been looking at it right now, what you're probably thinking is, all right, these lines are kind of curved, or at least they're kind of at an angle. But the reality is these lines are actually perfectly straight, and they are also all perfectly parallel. So it's a little hard, but if I can kind of let's see if I can kind of cover it up a little bit and move myself across. So right now I'm just pushing the side key. So what you notice is I'm moving straight across the screen, and that line is perfectly straight along with me. As I move across, here I go, right? Perfectly straight. And as I kind of cover things up, that line becomes straight. So what's happening here again, and this is what we're going to be doing as we go, is our eyes are getting the information that these lines are perfectly straight. But as we interpret it, what's happening is our brain is changing what we see a little bit. It's shifting it, it's organizing it, it's trying to interpret it in a way that makes sense. And so that's where we get these different things like optical illusions and why they work in general. So let's talk about this a little bit. So organizing our visual sensations. So again, all of this is about taking our visual information, that electromagnetic energy, and the neural impulses and adding to it. So our brain has this tendency, or it's really kind of its job, right, to integrate a whole bunch of pieces of information and create a meaningful whole out of it. Another term for this is a gestalt. So we talked about gestalt as the second wave of psychology at the very beginning of the year, which, if you remember, was this idea that we should be looking at the whole, or the whole person in that case. But again, the gestalt means a meaningful whole. So our eyes are receiving, and really our brain is receiving information from all of our senses at once. And what it's doing is it's taking all that information, it's adding it all together and trying to make it something meaningful, something that makes sense. And so again, we can kind of mess with this a little bit to try and figure out what it's doing. Now, there's a whole bunch of different ways that we do this. And we can call them like patterns or rules that our brain is going to use to organize the world. And that's what we're going to be looking at for really most of today, is what are these patterns or what are these rules that our brain is using to interpret our visual sensations, that information that's coming into our eyes. One example of kind of the things we're going to be looking at, I'm not going to tell you exactly why it is what it is, but one example is the image that we're seeing on the screen right now. So when you look at this, if I asked you, what is that an image of? And I gave you a little bit of time to look at it and kind of interpret it. What you would probably say, what most of you would probably say, is a cube. Right? Most of you would see a cube. Here's one face, here's another face, here's the top, here's the bottom, right? Here's either the back or the front, depending on the angle, and here's either the back or the front, depending on the angle. So we see this cube. Now, the reality is there is no cube there. This is all white. Everything here is white. There are only these black circles with the kind of chunks taken out of it. That's it. That's all the information your brain is getting. Yet, when we look at this, we see a cube, and not only that, we see it in 3 dimensions, even though these circles are perfectly flat. So what we want to do again is use things like this to try and figure out how is our brain organizing our world? How is it interpreting what our eyes are seeing? Because if we only understood, if we only perceived the literal things that we see, this would be just a bunch of random circles that are flat, and we wouldn't see this cube here. So why do we? That's kind of what we're going to be exploring here. So one way that we organize information, or one way that we interpret the information from our eyes, is through what is called figure ground. All right. Now again, all of this are ways that we are perceiving the world. So figure ground is basically this idea that when we get this information, we perceive some things as figures that are against or in front of a background, thus figure ground. So there's the figure in the front, and then there's the ground, the background behind it. So a really simple example, actually, if you look at the video of me right now in the top corner, I am a figure, you see me, in front of my wall and the map you can kind of see back there and my bookshelf. I'm the figure, that's the background, figure and ground. Now again, when you look at that, you know that I am sitting in front of all of those things. You know that I'm just not flat. So we can see the same thing here. If we look at these 2 images here, when you look at them, you probably see a figure in front of a black or a white background. Now what we can do with these different kinds of optical illusions is we can make it so it's equally viable to say either is the figure and the ground. And what we can do then is whatever we perceive as the background will change our perception of what the figure is. So let's use these as an example. So let's look at this image on the left first. I'm trying not to move so that little thing doesn't pop up in the corner too much. So if I look at this, let's pretend I have a white background. So that image is a white background, which is probably how most of you saw it at the beginning. If there's a white background, what you're probably seeing is a bunch of men that are black, right? They're entirely black, and they are walking down the stairs, and they're kind of like holding hands or something. Right? You can see their heads. Here's one head. Here's another. Here's another. Here's their arms. Here's their legs, and then here's the stairs. And I know this thing just walked out of the way. So here's the stairs. Now, if we switch this and we say this is actually a black background, you'll see that there's, instead of the black men, right, they're the background now, you're going to see white arrows pointing up. So here's an arrow right here, here's an arrow right here, and pointing down. There's one there, there's one there, there's one there. And you can kind of switch back and forth. You just perceive one as the front, one as the back, and the other one will kind of pop out at you. Now again, the information your eyes is getting is the exact same. We didn't change anything, we didn't do anything to this image, but all we did was shift what we are perceiving as the background, and that changed what we perceive as the figure. We can do the same thing here with this one on the right. So if we have a black background, what you're seeing is a white kind of like, I don't know, candelabra or a vase or something like that, right? Here's the top, here's the bottom here, and then there's kind of like some details. But if I assume that this is actually a white background, what you're seeing then is 2 faces. So here's the forehead, here's the eye, here's the nose, the mouth, the chin, and then the exact same thing on the other side. Chin, mouth, nose, forehead, and here's the eye right here. And again, once you kind of can see each of those, you can switch back and forth. So all that's happening is that we are perceiving one in front of the other. Now what's really important to remember is that when information gets to our eye, it's flat. There's no actual front or back to it. So this is a really important way for us to distinguish, all right, this is something in front of something else. Let's keep going here. Here's another example of the exact same thing. So do you see Wolverine, or do you see 2 Batmen kissing? Or they don't have to be kissing, but they're like chin to chin. They look like they're going to kiss. In front of a sunset, maybe. So if you see Wolverine, here's one eye, here's his other eye, here's kind of his little pointy head thing. I don't know what those are. Those little like giant eyebrow things he's got. Here's kind of like a pointy face cover. Here's his frown. This is his chest, right? Here's his shoulder and a shoulder. So there's Wolverine in front of this tan background. Now you could also see two Batmen that are nose to nose, and in front of like a little orange, kind of like an orange sunset. So here's one eye, here's the nose, here's the frown right here, here's his chin, and then the same thing on the other side, chin, mouth, nose, eye right here, and they're nose to nose. And again, the only difference between the two is what are we perceiving as the background? Again, figures and then the ground. Now, in addition to this figure ground, we also are going to use grouping. Now, we're going to look at all of these specifically in kind of like specific area or in specific depictions of each one in just a little bit. But we're also going to do some sort of grouping. So as well as being able to perceive, or at least trying to perceive something in front of being something else, a ground, right, a figure in a ground, we also are going to organize things into groups. And again, the idea is all of this stuff is trying to take a very, very complex world. Like if you just look around your room, there's a lot going on. There's a lot of complexity. So our brain is trying to take that complexity and organize it, place it into groups, and add some order to what's going on. So here's these 6 main ways that we are going to do grouping: proximity, similarity, continuity, closure, area, and symmetry. Now we're going to talk about each of these individually, except for I believe area and symmetry. Those ones should be pretty straightforward, but we'll talk about them for just a second. So area, for example, if I asked you what went together in that image right here, although I know I just blocked it with the little pop-up there, you would probably say it's one square within another. That's this larger square, and this smaller square is inside of it. That's our idea of area. There's 2 separate areas. This one is within this. They kind of go together a little bit. We also have something like symmetry. So if I look at this here, and I said break this into 2 pieces, what you would probably say is, oh, there's a diamond here and a diamond here, right? It's symmetrical. It's 2 of the same thing. Or you could say it's actually, this is a piece right here, this kind of arrow, and here's a top piece right there. There's another arrow. And what we're doing is we're saying it goes together. It makes sense because it's the same. It's the exact same on both sides. It's symmetrical. If I cut it in half, it looks exactly the same. So it goes together. And we're going to talk about these other kinds: proximity, similarity, and continuity and closure right now. But again, all of this is in ways that we group things together. We put things together. So our first one is proximity. So if I asked you, how many groups are there in this image here on the left? Right, what would you say? I'll give you kind of a moment to think about it. Now, if I asked you how many groups here on the right, what would you say for that? Now, when you were answering this question, it was probably a lot easier to do this side on the right. You probably immediately said 3, right? 1 group, 2 groups, 3 groups. Here's the groups right here. Where this other side, it was a little bit tougher. Now, the reality is these stars are the exact same. Right? They look the same, they're the same size, the same color. They're all the same on this side. The difference is they weren't really close to each other, right? They're pretty much all equal distance apart from each other. So it's a little bit tougher to decide what goes together. Where here, because we have these ones that are all next to each other, and they're further away from these ones that are all next to each other, and they're further away from these ones that are all next to each other, we naturally assume that if they're close by, they go together. That's proximity. Things that are near each other get organized together. Let's keep going here. So in addition to proximity, we have similarity. So let's look at the image on the left first. I don't want to move my mouse too far down, or that pop-up will come up again. If I asked you how you would group these together when you look at this image here, what would you say? Take a moment and think about it here. Now you're probably going to say, all right, I'm going to organize it into this circles, which is a diamond in the middle, and then these triangles on the outside. So here's one, here's another one, here's another one, here's another one, and then these all go together. Now, the question would be, why do we do that? These are all equally far apart. They're all the same color. I didn't tell you how I wanted you to group them together. I just said group them together. But what you're probably going to do, again, is based on similarity, you're going to group them by what is the most similar. So in this image, the most similar are these circles are all more alike than the triangles are, than they are to the triangle. That makes sense? So we see, oh, okay, here's a diamond in the middle, and then here's these kind of triangles on the outside made of triangles. So we naturally group them together. And even when you look at this, if I don't ask you to group it together, that's probably what you see. You probably see a diamond with these kind of triangles on the outside making a square. And again, we see that because of this proximity. I'm sorry, because of similarity. Now we can do the same thing over here on this side. So if I asked you again, how many groups are there in that image, and how would you group them together? What you're probably going to say, unless you're maybe colorblind here, is that this is one group here, this is one group here, this is a group here, this is a group here, and this is one here. Right, so we got 1, 2, 3, 4, and 5 groups. Now again, didn't have to necessarily mention anything about how you should group them or why you should put them together. You naturally do. We naturally put things together that are similar. Just like we naturally put things together that are in proximity or near each other, we're going to naturally put things together, group things together if they are similar to each other. Let's keep going here. So this next one, oops, no. That's not what I want to do. All right, well, just pretend you didn't see that. So this next one is continuity. So the question is this. When you look at this image, if I asked you to break this X into 2 pieces, how would you do it? Now, I know I kind of already ruined it for you guys. I kind of spoiled it here, but that's all right. What most of you do is you'd probably break it into 2 straight lines. This is one piece, and this is another piece. It's very unlikely that anybody broke it into pieces like this. So the question would be, why is that? And the reason why is what is called continuity. We expect when one thing is going a direction that it will continue on that direction. So because this is going in a straight or going this way, we expect it to continue going that way, not take a sudden right turn. Thus, these are the 2 pieces of an X and not this. We can do the same thing here. So if I look at this image and I said, okay, what if I moved this tree, what would I see? What am I going to see? If this tree disappears, what am I going to see? Now, most of you probably would have not answered this way. Now, you might have because I just kind of told you. But most of you would probably say, oh, this is one stick right here, and this is another stick right here. They're making an X behind the tree. But the reality is it's just equally as likely that it could be 2 that are kind of bent. Again, the idea is that we organize the world through continuity. So when something is going a direction, we expect that it will continue to go that direction, even though we don't necessarily have any information to confirm it. Our next one is what is called closure. So this is 2 examples of closure right here, and this is actually the same thing that we looked at on that not the very first page, the second slide with the cube. Second or third slide with the cube. So when you look at this image here on the left, the question is, what do you see? Now, the answer for most of you is probably a soccer ball, right? You see the circle here, here's the edges, here's the different, the colored squares. Now, the reality is there is no soccer ball there. That is not a soccer ball. It's just kind of some weird shaped hexagons. There's like one actual, I'm sorry, not a hexagon, a pentagon. Well, there's actually 1 or 2 real pentagons and then some kind of curved ones with nothing else. Yet you can probably almost make out a line that goes all the way around. That's this idea of closure, that we expect objects to be closed, to be contained. So another example is on my right here. So when you look at this, I could ask you, how many triangles are there? How many triangles are there in this image? I'll give you a second to kind of count them up. Now, if you said anything that wasn't 0, you're wrong. There are no triangles in this picture because there is nothing here. There's no line here. There's no change in shading. This is all perfectly white. If I kind of move that right there, it's perfectly white. These aren't triangles because there's only 2 angles. These are just angles. This isn't a triangle because there's no bottom here. There are no triangles in this picture. Yet, when you look at it, it feels like there's a line. Whoops, I just went too far, sorry. It feels like there's a line that runs right down here, one that runs across, one runs across. And it looks like there's a triangle sitting on top of another triangle with maybe circles underneath it. And the reason we're seeing that again is closure. This idea that we expect shapes to be closed off, to be separate. So we connect these things even though there's nothing here. And again, it's this idea of our perception is organizing and understanding things. So even though there's no visual information, your eyes are not getting anything that should say that this is a triangle, our brain kind of adds it in. And that's why you can almost see these lines. It's almost like they're 2 different tones, even though there's not. So again, the way we're organizing our world, this way is closure. Now we can also talk about depth perception. I'm going to put myself right here, that way YouTube doesn't get mad at me. So depth perception. This is an additional way that we are organizing or interpreting our world. So depth perception is our ability to see objects in 3-dimensional space. Now again, what's really important to understand is that images that strike our eye, the information that comes into our eye, is 2-dimensional. It's flat. And we can think about that because our retina is flat. So you can think of it like a projector screen. When that information comes in the eye, it gets projected onto that retina, just like a movie gets projected onto a screen. Now, a movie screen is flat. It's 2-dimensional. And that's the exact same thing with our eye. It's flat, well, it's curved, but it's a flat surface. It's 2-dimensional. So depth perception is something that our brain is adding in to allow us to see things in 3 dimensions. Now, one of its most important jobs is allowing us to judge distance. So for example, this image here on the right, if I asked you what is closer to you, this kind of section right here, or this section right here on the outside, what would you say? If I said, again, which is closer to you, this right here, this outside layer, or this one right here, what would you say? Now again, the answer is neither. They are perfectly flat. You're literally looking at this on a computer screen that is perfectly flat. They are the exact equal distance away from you. But it looks as if this central part is further away. And the reason for that is that this image is using different cues that our brain uses to judge perception. So we're tricking our brain into seeing this as being further away than this. So we're going to talk about how this actually happens and why this happens. Let me move myself out of the way here. So depth perception, there are 2 types of cues that we use to understand depth. The first one, or the first type of cues, are binocular cues. So binocular cues are cues that depend on the use of both of our eyes. So basically it works like this. Our eyes are about 2.5 inches apart. So if there's a gap between your eyes, right? They're not literally touching each other. They're separate. So when information gets to our eyes, it's slightly different. Just very, very slightly different. And a really easy way to like look at this is if you just look straight ahead and then you like close one eye and just open, just like go back and forth like this. And what's going to happen is the image is going to kind of shift a little bit back and forth, or it might turn a little bit depending on what you're looking at. And you can even do that with the screen, right? So again, just close one eye and then just open and close them back and forth, and you'll see that image shift a little bit. So our eyes are each receiving a slightly different picture of the world, a slightly different image. So our brain takes that slightly different image and it basically kind of like calculates the distance. So we know the bigger the difference, the bigger the shift between the two eyes is, the closer it is to us. The less the difference, the less the shift will be. And you can just do that really simply. If you take something and you like hold it up to your face and you close your eyes back and forth, and then you look at like a picture on your wall and you do the same thing, the picture on the wall isn't going to move as much as the thing that's right next to your face. So our brain is kind of doing like a little calculation to determine, okay, this is really close, this is far away. So that's one way of depth perception, or a binocular clue. Now we're going to use a little activity. This is called like they call it like the finger sausage, or the floating finger sausage, or something like that. We'll do this during class, but that's what we're showing here. So we'll talk about that a little bit later. Now, in addition to binocular clues, we also have monocular clues. So monocular clues are depth cues that are available with just one eye. So a binocular clue, if you like didn't have an eye, like if you were missing an eye or one eye didn't work, you're not able to use those binocular clues because you need to have both eyes. With a monocular cue, you are able to see it even with only one eye. So it's available to each eye separately, basically. Now we're going to talk about these monocular cues specifically as in just a moment. Now there are, 7 of them. Relative height, relative size, relative clarity, interposition, linear perspective, light and shadow, and relative motion. Now again, we're going to go over each of these specifically in just a moment, but those are our monocular cues. This is an example we're going to do in class, so I'm just going to skip it here. Okay, so we're going to start looking at these a little bit. Where can I get out of the way? I think right here should be fine. So our first that we're going to look at, our first monocular clue, is what is called relative clarity. Relative clarity. Let me move myself out of the way. So if I look at this painting, again, we're talking about depth perception here. So what I want to know is what in this image is closer to me. Is it this dock right here? Is it the dock? Or is it this building right here? This kind of tower. Which one is closer to me? Now again, technically speaking, they're the exact same distance. Because again, technically, this is a painting on a screen that is perfectly flat. Yet you can probably really easily tell that this building would be much further away than the dock. So the question is, how do we know that? And what we're using is this idea of relative clarity. So when something is further away from you, it gets blurrier. It's harder to see, it's harder to make out. When something gets closer to you, we can see a lot more detail, it's easier to see, it's easier to make out. So we assume that if something is easy to see, if it's more detailed, it is closer to us than if it's far away. That's this idea of relative clarity. Again, something that's far away it's harder to see details. Something that's close up, it's easier to see details. So we use that then to help us determine what's close and what's far. So relative clarity. Let's look at another example here. So the next example is what is called linear perspective. Linear perspective. So if I asked you when you look at this image, and I said, what is closer to you? This section right here, or this section right here of tracks? Which one's closer, this section at the bottom or this section at the top? Now, what you're all going to say is this section at the bottom. And the reason for that is what is called linear perspective. So all that's happening here, and this is, if you think about it this way, if you think about this as a flat image, as a painting on a piece of paper, all you're doing is you're drawing two lines that are going up straight into the air for some reason and getting closer and closer together until they finally reach each other. What happens though is in our brain, when we look at something that's straight, if you look down a really long road or you look down railroad tracks like this, as it gets further and further down, it seems like they're getting closer together. Right now we know obviously railroad tracks are literally parallel. They can't come together like that. But because they're further away, it appears like they're merging, like they're coming together. So because of that, our brain uses that as a cue to understand that this is further away. That because these two parallel lines are getting closer to each other, we know that this is farther away than this. And again, all of these things are monocular clues that allow us to understand depth. Let's keep going here. This next one, we're going to look at relative size and relative height. We're going to do both of these kind of together. Oops, clicked on the wrong thing, sorry. So, here we are. So we have this picture here of these two men sitting in chairs in a hallway. So there's two questions I want to ask. The first one is, which of these two men is closer to us? The man in the red shirt or the man in, I think this is a white shirt or maybe a light blue, whatever. Man in the red shirt, man in the, let's say, blue shirt, or let's say white shirt. Who is closer to us? Now, once you have that decided, would you guess that these two men are basically the same size, or is one far larger than the other? Now, again, I mean basically the same size. I don't mean they're the exact same height, but they basically the similar size, or is one much, much larger than the other? Now, when you answer that, you probably said, okay, guy in the red shirt is closer to us, and they're probably about the same size. Now, here's the thing. This image here that I'm bringing up right now, although it's taking a very long time, is the exact same image. All we did was copy paste this guy out and put him right here. So when your eye gets the information from this is the exact size as this man here. So the question is, why do we assume, or how do we know that they're the same size? And you can actually like measure this if you take something right now and you measure this guy here and you measure this guy here. They're literally the exact same size, even though it looks way smaller here, right? So what's happening is this, is that when we look at something, we know that the further something is away from us, the smaller it looks. So even though this guy is much smaller, like the literal information that our eye is getting from this figure is much smaller than this one, we perceive them as the exact same size. But when we take that exact same piece of information and we move it so it's in the same, plane as this other guy, suddenly he looks really, really tiny. Again, all that changed was where we put him. That's it. It's the exact same information, exact same picture. He's the exact same size as he is here. So again, what we're trying to do is pull apart that perception to understand that even though we're collecting this information, our brain is doing a lot of things to make it make sense in our world. Because in our world, when something's further away, it's smaller than something that's close up. Let's keep going. Let's look at light and shadow now. Let me move myself out of the way. Oops. So we look at this image here on the right now, and what I want to know is which of these ovals is basically like, if you think of them as like dented out versus dented in. So we've got all these little ovals here. You can see them all. Which ones are dented out and which ones are dented in? I'll give you a second to look at that while I take a drink. Now, what you're probably going to say is that these ones right here are dented out, and these ones right here are dented in. So the question I would ask is, how did you know that? How do you know that they're dented out versus dented in? And what you're going to say is the shadow, right? Is that the ones that have the shadow at the top, we know must be dented in, and the ones that have the shadow at the bottom must be dented out. So I'd ask, okay, well, how do you know that's true? And the reason this works, even without you thinking about it, is that in our world, light comes from above us. The sun is above us. So when the sun shines down, if something has a shadow, that means that it is blocking that light. So this must be dented in, because as the light comes down from here, this part is darkened, so it means it's blocking the light. This part is bright, so it's receiving that light more. Same thing here. We know this is dented outwards because that light is hitting this this top layer here, and it's being blocked by the bottom. Now what's interesting is this. Oops, I don't want to do that. Let me get out for a second here. If I take this and I flip it exactly upside down, what you might notice is that they work the exact same way. Now look, all of the ones that were originally sticking out are now dented in. And all the ones that were originally dented inwards are now sticking out. Again, all I'm doing, and I can maybe do it again for you, I'll keep it right here. Can I not grab it? Here we go. So let's flip it upside down again. So let's pay attention to this dot right here. So when I move him, he's going to go down here, right? So if I just look at just this corner dot, I flip him all the way over, and all of a sudden he's sticking out. Flip it back, dented in. Again, all that's changing in that image, the only thing that's different is where where that shadow is. So because we assume that light comes from above us, it means that this must be going inwards and this must be going outwards. Again, we're adding in that perception art. We are taking what we know about the world or what our brain knows about the world, and we're adding it in to help organize and help understand the information that our eyes are receiving. Our last section here, so our last two. Our first one here is what is called interposition. Interposition. So when you look at this image, I could ask you which of these shapes is on top or nearest to us, however you want to think of it. Which of them is on top? You're probably going to say blue right here. And I could say which one is in the back. You'd probably say yellow. Now, the reality is again, this is a perfectly flat image. It is equally likely that these are all next to each other, right? That this is one triangle, this is one kind of like, I don't know what that is, a hexagon or some kind of quadrilateral, right? Here's another triangle here, here's another triangle here, here's another triangle here, and here's one here, and they're all separate shapes. But, right, we're kind of adding two different things. We're keeping this idea of continuity, that this is a shape and it's red and it's going the same direction, so it's got to be one shape, and this is one shape and it's yellow and it's going one direction, so it must be one shape. And here's our blue one on top. And in addition, we know that if something is being blocked by something else, it must be behind it. So because the red is being blocked by the blue, we know it must be behind the blue. And because the yellow is being blocked by the red, it must be behind the red. So that means blue is in the front, red is in the middle, and yellow is in the back. This is the idea of interposition. So whatever is blocking something else is in front of it. Now, this is really important because we know that, again, things are continuous, they tend to stay together, and that something can be behind something else. And this is why, like, when you guys, this is a little tough because we're not in a classroom, but if you look around your room right now, and let's say like you're sitting at your desk, I don't know if you have a desk or not, but imagine you're sitting at your desk and you're looking at your laptop. You know that your desk is still behind your laptop, right? But it's still one piece, it's still a desk. We know that it doesn't just end or become something else. So that's this idea of interposition, that one thing is just in front of the other. Our last one is what is called relative motion. I'm clicking on the wrong thing. Here it is. Relative motion. Let's move myself over here. So when you look at this image here, what I want you to pay attention to is the movement. So when you look at this, if I look at the stuff at the bottom, and I compare it to the stuff in the middle, and then I compare that to the stuff at the top, right, I can ask, what is the difference? And what you're probably going to notice is that the things that are closest to us are moving the most. They're moving the quickest. They're flying by us the quickest. And as things get further away from us, it moves slower and slower. And something that's really far away, if that's like these mountains, it actually kind of looks like it's moving with us a little bit. Now, this isn't a super long GIF, so it's not like perfect here, but you can see the mountains don't really look like they're moving, or they look like they're moving with us. That's this idea of relative motion. that things move in motion with us relative to our position. So this is like if you're driving and you look out the window, you'll notice this, right? That the things that are really close tend to be moving really fast. And as something gets further away, it looks like it's moving slower and slower and slower and slower until eventually it either stops or it moves like it's slightly moving forward with you. And that's this idea of relative motion, is that when we see the difference in that speed and how it's moving, we know how far away it is. Now this is obviously a video, but you can do this exact same thing, or again, this is something that's flat. Like there's no actual depth here. But we perceive this depth. We can tell that this mountain is far away because of how it's moving compared to everything else. Let me move myself out of the way here. Okay, so here's this image. Now, what we want to look at here is how is depth being made in this image. So when you look at this, if I asked you, are all these little Lego guys the same basic size, what would you say? And if I asked you how far away do you think the, let's say like this guy's head here, how far away do you think that is from where the people are standing? What would you say? Now all I'm going to do is I'm going to show you this exact same chalk drawing, but I'm just going to show you it from a different angle. So this is the same exact image, except for we changed the angle. Now suddenly look, some of these are way larger than the other ones. And everything is really stretched, right? It looks like everything's much longer than it was here. Right? When you look at like the staff, I think is a good example. So it doesn't look that big here. All of a sudden, it looks huge. Same thing with this guy and this horse, right? It looks huge, where if I go back, it doesn't look that big. So what's happening here is to give this perception of depth, what they're doing is they're stretching these pieces out, right? So they're way bigger. That way it takes up more space. Whoops. That way it looks like it's sitting up. It looks like it's standing. So at a certain, from a certain angle, right, we see depth in this. Let's keep going. So in addition to depth perception and all those different cues that we looked at, we also have what is called perceptual constancy. So we've got figure ground, we have grouping, we have depth perception, and we have perceptual constancy. So perceptual constancy, and I'm pretty much just going to read the definition for you right now, is perceiving objects as unchanged, having consistent shapes, sizes, lightness, and color, even as illumination and retinal images change. So again, we expect things to stay the same, even as the literal information we're getting from our eyes changes. So a simple example, let's start at the image on the left. So if you're looking at those two tables, the question is, which of those tables is longer? The one on the left or the one on the right? Now the answer to that question is that they are the exact same length. Now I obviously can't do this for you, but if you want to right now, you could pause it and grab a ruler or a pencil or something. And if you measure this side right here, it is the exact same length as this side right here. Literally exactly the same. I've done it with a ruler before. You can do it right now. So the question is, why does this one look so much longer? And again, the answer is this idea of perceptual constancy, that we perceive things to be the same. So because this looks long here, we assume that if we turn it and we change the angle, it will be the same length. We expect size not to change. And again, this has to do with the idea that in our world, right, a desk doesn't get bigger or smaller depending on the angle you look at it from. It's always the exact same size. Let's do another example I think is a little bit nicer even. I want you to look at this image here on the right. So we've got all this checkered tile floor. We've got this little cylinder, and then we've got tile A and tile B. So my question is which of the tiles is darker, A or B? Take a few seconds to look at it. Again, which is darker, tile A or tile B? Now what I'm going to do here, and this is the only thing I'm doing, is I'm literally just going to cover up everything except for tile A and tile B. Okay, so you're going to see these like white squares come in. You can see them fading in right now. So all I'm doing is I'm covering up A and B. Now, as everything's covered up, what do you notice about the color of those tiles? They're the exact same color. Now again, all I did was cover up everything else around it. So tile A and tile B are literally the exact same color. Your eye is receiving the exact same color information for A as it is for B. So the question is, when I look at it, why does B look so much lighter? Why does B look like it's a white tile in shade, and A just looks like a dark tile? Why do we see two different things? And again, the answer is this idea of perceptual constancy, is that we know if there's a shadow on something, it doesn't change color, even though it looks differently. So our mind compensates for that. So because B is in shadow, we assume that it's actually a lighter color than we're seeing. And because A is well lit, we're assuming it's a darker color than we're actually seeing. And so what happens is, even though your eyes are getting the exact same information color-wise between A and B, again, if I cover them up here, the exact same color, when I have all of the perceptual information around it, I add it in and my brain literally changes the color of it. Okay, so again, one more time. Here's A and B. They look totally different. A looks dark, B looks light. Cover up everything else around it, and suddenly they're the exact same color. So this is the idea that things do not change even if the retinal image changes, the information our eyes receive changes. So we compensate for that. Oh, and again, maybe before we go on, I think this is a really nice time to kind of come back to that quote from the very first day of we do not experience things in reality. We experience them as it's useful for us, right? We do not perceive information as our senses as a reality, but as it's useful for us. This is a really good example. The reality is A and B are the exact same color, but we do not perceive them that way because it's not useful to us. Let's continue on here. Perceptual adaptation. Now this one is usually a nice little experiment that we do, but we can't really do it because we're not in the classroom. But all this is perceptual adaptation, and we've actually talked about it before. When we talked about sensory adaptation, it's very similar, but it's basically this idea that we are able to adjust to changed sensory information, to change sensory input. Now I'm going to show you guys a video of this in class. It's going to give you an example of how we do this, but I'm going to give you another one right now. So I mentioned in, I think both classes, but at least one of the classes I mentioned that I technically have a little bit of a lazy eye in my left eye here. Now it's not like so much that it doesn't like float away or anything, but I have trouble focusing. So my right eye is like my dominant eye. So what happens is really when I'm looking at stuff, I'm actually seeing everything just slightly shifted over to the left because I'm getting more information from my right eye than my left. Now, it would seem like that would mean I wouldn't be able to do things like play sports or like wrestle or play soccer or stuff like that. But what's happened is because I've had that my whole life, I've basically just adapted to it. So I still like catch and run and do all those other things like totally normal because I've basically adapted to the idea that my depth perception is a little bit off. So we're going to see, like I said, a video of this where we're going to watch someone where they put on goggles. I have some of them. If we're ever back in the classroom, I'll do a little experiment for you guys with them. That's basically going to switch their senses. So what it's going to do, I believe the ones he has, is going to flip what his vision completely upside down. And so what we'll see is as they continue to wear those, they'll slowly adapt to the point where it's just normal, where they're just able to function pretty much the same as if they weren't wearing these goggles that are changing. So we slowly adapt to the sensory input information. Again, this is that's what I was talking about right there. So that's going to wrap up this section of sensation and perception. again, take a little bit of time and go ahead and do a nice summary for us, just wrapping up everything from this video.